In this tutorial, we're going to look at 3 examples of limits that involve compound fractions. Compound fractions are expressions that have fractions within fractions, as each of these do. So we have an overall fraction with 2 fractions in the numerator. Now, the general strategy for these limits is going to be to simply simplify as much as possible. Typically, if we reduce to a single fraction, then we will be able to then evaluate the limit via direct substitution. Other techniques may be required along the way. We'll take a look and see what happens. So let's start here. So the general strategy, as I mentioned, is to rewrite and simplify algebraically as much as possible. So remember, don't forget your limit notation. So we have the limit as x approaches 3. We're going to continue to write that limit notation until we actually take the limit via substitution. Now, I want to combine this to get a single fraction. There's probably 2 basic ways you can do that. You can get a common denominator between these two and multiply to achieve that common denominator. Or if you want to, you can multiply the numerator and denominator of the overall fraction by the least common multiple of these 2 fractions. So the least common multiple of the 2 denominators, the least common multiple here would be 3x. So if I multiply the numerator by 3x, the overall numerator, and multiply the overall denominator by 3x, that should do the trick for us. Or we can simply get a common denominator for these 2 fractions, and that will achieve the same thing. So maybe let's do that way first, and then perhaps I'll do the other way I mentioned for one of the future problems. So let's see. The common denominator here, as I mentioned, is 3x. So I need to multiply this fraction by 3 over 3. And multiply this other fraction by x over x. Remember, if you multiply by, say, x divided by x, or say 3 over 3, well, you've multiplied by 1, so you've not changed the value of the expression, which is very important. Now, we have a denominator of 3x, a denominator of 3x, so we can combine these 2 fractions to achieve 3 minus x over 3x, of course, over the overall denominator of x minus 3. Okay? Now, recall, we have a fraction divided by an algebraic expression. When you're doing division with fractions, you take the reciprocal of the divisor and multiply. So we can think about this. It's kind of weird. Some students get confused because we have a fraction and then a non-rational expression. But if you think about this denominator as being a fraction with a denominator of 1, well, then it makes sense that, okay, we have 2 fractions, and how do you divide? Well, you take the reciprocal, you flip the divisor, and multiply. So what does that leave us with? If we flip the divisor and multiply, we're going to have 3 minus x over 3x times the reciprocal, which is 1 over x minus 3. Okay? Now, we almost have a nice cancellation here. Almost have a nice cancellation. We still can't use direct substitution, and I guess I didn't mention this earlier, but probably most of you have noticed this by now. Direct substitution would not work in the original function, because if I try to substitute 3, I get 1/3 minus 1/3 on the numerator, which is 0. But on the denominator, I get 3 minus 3, which is 0. So I get 0 over 0 indeterminate form, which means we need to do some further investigation into this limit. Clearly division by 0 is undefined. We cannot say, one of the biggest problems I see, the biggest mistakes I see with students, new calculus students, is they say, oh, the answer is 0. But 0 divided by 0 is not 0. That's indeterminate. We need to do some sort of manipulation so that we can then take the limit via direct substitution. Now, we still have the same problem we had before. We've manipulated this expression, but we still cannot use direct substitution, because if we try to directly substitute, I still get a 0 on the denominator. However, notice that I almost have the cancellation I'm looking for, but these do not match up currently. We have 3 minus x on the numerator and x minus 3 on the denominator. Those are not the same expression. But if we factor the numerator, or I suppose the denominator, but I'll factor the numerator, we can make those expressions match. Now you might say, well, there's nothing really to factor on the numerator, and there's not much. You're right. But you can always factor out a negative sign if you like, and I'll do that. Factor out a negative sign, and if we do that, that reverses the signs of those two values, and so we have negative 3 plus x times 1 over x minus 3. And now you see, well, negative 3 plus x is in fact the same thing as x minus 3, so we can divide out those common terms, which leaves us with the limit as x approaches 3. Now on the numerator, we're left with a negative 1. And on the denominator, we're left with a 3x. So it looks like we are now able to use direct substitution, because now substituting in a 3 does not cause any problems, does not cause division by 0. So we can now substitute, and we can drop the limit notation, because we are now taking the limit, and we hit negative 1 over 3 times 3, which of course is negative 1/9. Okay. Again, notice that's basically all algebra. Basically all algebra. Okay. That's why it's very important to have very sharp algebra skills when you're in calculus class. Okay, let's take a look at the middle one. So here again we have a compound fraction. We have these two fractional expressions in the numerator, and of course an overall fraction. We're going to follow the similar strategy. The idea is to eventually get this to a single fraction, a single numerator over a single denominator, and perhaps a few nice cancellations along the way. We should note that direct substitution fails. If we try to substitute 4, you get a 0 on the denominator, 4 minus 4. And you also get a 0 on the numerator, because 1 over the square root of 4 is 1/2. 1/2 minus 1/2 gives you 0 also. So again, this is 0 over 0 indeterminate form. Now, I mentioned on the first problem that there was another way we could have started off simplifying, and that is to multiply by the least common multiple of these two denominators. In this case, the least common multiple of these two is just 2 square roots of x. So if I multiply by, here I'll save myself a little room here and just start off doing this. If I multiply this by 2 square roots of x on the numerator and 2 square roots of x on the denominator, well, okay, I've multiplied by 1. And let's see how that affects the numerator. It should make the numerator come out a little nicer for us. So let's see what happens. Of course, we rewrite our limit notation. The limit as x approaches 4. We can go ahead and write the denominator because we're not really going to do anything with the denominator. We're just going to rewrite it essentially. We will need to put parentheses around the x minus 4 since that has 2 terms to it. But x minus 4 times 2 square roots of x. Do not distribute that when you're working problems like this because it will cause problems later. Okay? We're going to look for a specific cancellation in a few minutes, and if you distribute the denominator, well, then you won't be able to notice that cancellation that we're after. So there's our denominator. Now, how does the numerator play out here? Well, I have 2 square roots of x times those 2 terms, so I need to distribute. So 2 square roots of x times this first fraction would give me 2 square roots of x over the square root of x. And then I need to multiply negative 1/2 times 2 square roots of x, which that just gives me 2 square roots of x over 2. And then we can, of course, do a little bit of simplifying with those 2 fractions. The purpose is that now the numerator should not contain any fractions. 2 square roots of x over the square root of x is just equal to 2. 2 square roots of x over 2 is just equal to 2 minus the square root of x. And of course we have our denominator as well. X minus 4 over 2 square roots of x. Now, on the last problem, when we basically got to this step, now I took a longer route because getting a common denominator and such just takes a few more steps. I prefer multiplying by the least common multiple of the 2 denominators. This method's a little faster. However, I did that on purpose here because this problem is just longer in general. Because now I don't have any cancellations. I don't have any factors common to the numerator and denominator. Don't make the rookie mistake of trying to cancel off that square root. That is an algebraic mistake because the top is not factored. But I think what we can do is employ a strategy that we've talked about before, which is rationalizing the numerator. So let's see what happens if we multiply the numerator by the conjugate of the numerator, and of course we have to multiply the denominator by the same value. So we're going to multiply by the conjugate of 2 minus square roots of x. 2 minus 1 square root of x, which is 2 plus square root of x. Of course, divided by itself. We have to multiply by 1 there. If you don't multiply by the same expression over itself, you're not multiplying by 1, and thus you're changing the value of the expression. So, we have 2 terms in each of those expressions. So we need to put parentheses, and we're going to then multiply. FOIL would be the common term. Technically, we're using the distributive property a couple times. Now, if you have multiplied conjugates before, which I'm sure you have, you will know that the 2 middle terms will always add to 0. I will write out all 4 of the terms that we acquire, but in the future, we probably won't do that since we know the 2 middle terms will add to 0. If you multiply 2 times 2, you get 4. 2 times the square root of x is just 2 square roots of x. 2 times negative square root of x is negative 2 square roots of x. Then we have negative square root of x times positive square root of x. That gives us negative square root of x squared. And now for the denominator, Again, we're not going to distribute. It's going to look terrible for the time being, but the denominator will eventually take care of itself. So we're just going to write x minus 4, 2 square roots of x, and then we're going to multiply now by 2 plus the square root of x, and just leave it alone. Don't distribute, don't FOIL, don't do anything. And now let's see what we can do with the numerator. The limit as x approaches 4. Let's just go ahead and rewrite the denominator. And now what happens on the numerator? Well, those add to 0, since they are opposites. And then we have 4 minus the square root of x squared is simply equal to x. So we have 4 minus x. Okay? So we have kind of run into the same situation we ran into right here. We have almost the cancellation we're looking for, but not quite. We have 4 minus x, x minus 4. How can we remedy the situation? Well, we'd factor out a negative sign. So we get the limit as x approaches 4. Oh, there is no equals right there. We factor out a negative 1. That gives us negative 4 plus x, or we can just write x minus 4. That looks a little better. Over x minus 4. Then we have 2 square roots of x times 2 plus the square root of x. And now we see we have the long sought after cancellation, which that gets rid of the x minus 4 factor on the denominator, which was causing us all of that grief. Now we should be able to use direct substitution without issue. Let's rewrite the function one more time before we use direct substitution. This is our cleaned up function. We have 2 square roots of x on the denominator times 2 plus the square root of x, like so. And you notice that now substituting in a 4 causes no problems. That is, it doesn't cause a 0 on the denominator. That's the problem we're talking about. So let's see what happens when we substitute. We still just have a negative 1 up top. And we have 2 times the square root of 4 times 2 plus the square root of 4. Which is, oh, we need a little more room here, negative 1 divided by 2, well, square root of 4 is 2, so 2 times 2 times 2 plus the square root of 4, well, the square root of 4 is 2, so 2 plus 2 is 4. So we have negative 1 over 2 times 4, which I suppose that gives us negative 1 over 16. Negative 1 over 16. Again, that took a little work, but it's just a lot of algebra. All there is to it is algebra. You'll find this theme is true with a lot of things we do in calculus, that we have maybe a calculus concept or technique, but underneath it's just a lot of algebra. That's what you have to do, practically speaking. Okay, now let's look at this last one. Again, a compound fraction, and we have the limit as x approaches 0. So if we try to use direct substitution immediately, well, clearly the bottom just has an x on it. So if we try to use direct substitution, the numerator turns to, the denominator turns to a 0. But I think you'll also see that the numerator turns to a 0 also, because 0 plus 1 is 1, 1 squared is 1, 2 over 1 is 2, 2 minus 2 gives you 0. So again, this is exactly the same indeterminate form we've seen so far. So, equals a limit as x goes to 0. And let's see what we can do here. I think I'm going to use the same technique of multiplying by some expression over itself, a specialized version of 1, so that I eliminate the fraction on the numerator. Now in this case, this is a little different than the previous two examples, because the previous two examples had 2 fractions in the numerator. This one only has 1 fraction in the numerator. Of course, you could think about this as negative 2 over 1, if you wanted to get a common denominator and combine. Or let's think about it this way. What if I multiplied that expression by this special version of 1? X plus 1 squared divided by itself. So I've multiplied by 1, just like I did here, just a special version of 1, because when I do that, it's going to allow the fractions here, this 1 fraction, to be eliminated. Now, I'll rewrite the denominator first. We don't want to try to distribute or expand it in any way. We're just going to write it as x times x plus 1 squared. Now the numerator, we have a single term multiplied by 2 terms, so we do need to recognize that there needs to be parentheses right there, and now we need to distribute. So we have 2 over x plus 1 squared times x plus 1 squared. Minus, so I should have had a larger fraction here, minus, and then we have x plus 1 squared times 2. So 2 times x plus 1 squared. Now, notice, cancel, cancel, which eliminates the fractions on the numerator. So now we have the limit as x approaches 0. I'll just go ahead and rewrite the denominator. We do not want to expand that, just leave it alone for the time being. Now what's left on the numerator? Well, we have a 2 is what's left over here, minus 2 times x plus 1 squared. Okay. And there is no cancellation currently that we can make. Don't try to cancel out x plus 1 squared and x plus 1. The numerator must be factored in order to make that cancellation, and it's not currently factored. I think now what needs to happen is we should expand this expression and just see what happens. I think if we expand this expression and then collect like terms, eventually we'll have a few things that add to 0 perhaps, and then we'll have a cancellation that we can work with. Limit as x approaches 0. Now if you want to, this might make it go a little faster. I don't know. If you factor a 2 out of the numerator, that might make our arithmetic a little easier and algebra a little easier. Notice this has a 2 and that has a 2. So if we factor a 2 out, what are we left with? Well, there'll be a 1 right there, minus just that expression, x plus 1 squared. I'm not sure that's going to save us that much time, but it'll save us maybe a little bit of time. x plus 1 squared on the denominator equals a limit as x goes to 0. Now we have a 2 times 1 minus something. Now, here's again where you have to be careful with your algebra. I'm going to say that over and over. You're going to be so sick of hearing that. But you have to be careful here. I think they call it the sophomore's dream, or maybe it's the freshman's dream, that a lot of students want to say this. A lot of students want to say x plus 1 squared is equal to x squared plus 1 squared. You might be guilty of that yourself. But remember, that is not true. X plus 1 squared instead is equal to x plus 1 times x plus 1, which we need to use the distributive property, or if you want to call it foiling, that's fine too. So x times x is x squared. X times 1 gives you x. 1 times x gives you x. 1 times 1 gives you 1. And if you collect your like terms, you get x squared plus 2x plus 1, not x squared plus 1. So x squared plus 2x plus 1. And we have to be careful because that subtraction sign applies to that entire expression. So if we need to use parentheses here, and that is x squared plus 2x plus 1, like so. Okay? Equals limit as x approaches 0. We still have a 2 out front. And then we have 1 minus, distribute your negative sign, x squared minus 2x minus 1 over x times x plus 1 squared equals limit as x approaches 0. Notice positive 1, negative 1. And then we have 2 times negative x squared minus 2x. What can we factor out of this expression? Well, we could factor out, say, a negative x, or we could factor out just a plain old x, whichever you prefer. Let's factor out a negative x. If I factor out a negative x, that would give me a negative 2x out front. And what would be left here? So if I factor out a negative x, I would just have x left over, and a negative x factored out here will leave us with x plus 2. Okay? Just to make sure that your factorization is correct, if I distributed a negative x, I would have x times negative x squared. 2 times negative x would give me negative 2x. So yeah, that's good. Now the reason I factored out an x, or a negative x, is that now I have a nice cancellation. X factored out on the numerator, x factored out on the denominator. I can divide those out, which leaves me on the numerator with negative 2 times x plus 2 divided by x plus 1 squared. And I think that that cancellation, that when we divided out those x terms, that was the term that was on the denominator causing us the trouble. And now notice that direct substitution should not cause any problems. 0 plus 1 is just 1, which is on the denominator, is not a problem. So we can now use direct substitution. I'm going to stop writing limit, because as soon as you take the limit via direct substitution, you can stop writing the limit notation. In fact, you should stop writing the limit notation. So we get negative 2 times 0 plus 2 over 0 plus 1 squared. Simplifying the arithmetic here, we have on the top negative 2 times 2, which is negative 4. On the bottom, 0 plus 1, 1 squared, so negative 4 over 1, or we can just say equals -4. And there we have it. Again, notice how each of those took a substantial amount of algebra. So, I'll say it one more time for this video. Make sure your algebra skills are in tip-top shape. Here, our strategy was, broadly over all three problems, was to eliminate the compound fraction, which you can do by getting common denominators for your two smaller fractions in the numerator, or you can also multiply by the least common multiple of those two denominators to achieve the same result. The middle problem took us a little more work because of the radical involved, the square root. We also had to rationalize the numerator. This one, we had to do a little bit of expanding and collecting like terms as well. If you have any questions, always feel free to ask. Until next time, see you soon.